Now, come to example 3. Just one thing that we have seen just 2 examples, and from that you assume that how much time it takes to explain that each and everything, right. And but try to understand, hopefully when I will go on giving the numericals, 1 or 2 things I will leave up to you, that explanation, right. When we will this thing, you only 1 or 2 cases I will put a question to you that why it is coming, because if everything I tell, then you have to then you will not imagine many things. So, 1 or 2 things I will skip. For example, this example, one particular thing I will just leave it to you, that you find out that what is the reason, right. I will give everything in details and I will give you some hint, but you find out what will be the reason. For example, take this example that first time this thing, then I will explain this, right. So, a single phase 50 Hz power line is supported on a horizontal cross arm. The spacing between the conductors is 4 meter. A telephone line is supported symmetrically below the power line as shown in figure 14. This is figure 14, I will come to that. Find the mutual inductance between the 2 circuits and the voltage induced per kilometer in the telephone line if the current in the power line is 120 ampere, right. Now, it is basically assume it is a single phase line. So, this is 2 conductors, this is incoming, this is your what you call outgoing, that is why current here is I, here it is minus I, right. That means one is going into the page, another is leaving the page, this is the convention. So, between these 2 conductors P1 and P2 power line, that distance is 4 meter, right, and these 2 are nearby telephone lines, right. So, from this conductor the distance is D2, this is D1, from it is symmetrical, this is symmetrical. So, here also this is D2, this D2, they are same. Similarly, this D1 they are same, and from here to here vertical distance is 2 meter. But now you have to find out D1 and D2, first you find out. So, power and telephone lines for the example, right, and you have to find out voltage induced in the telephone lines, right. So, first thing is that D1, you have to find out that what is your distance D1, right. So, this is 2 meter, your what you call this is 2 meter, right, and this one your it has gone, this is your, this height is this vertical line you will draw, this is 2 meter, right, 2 meter, and from the, and this one your from I mean I just hold on, I have to make it for you. So, this is the conductor P2, say this is conductor P2, right, draw a vertical line, this distance is 2 meter, this distance is 2 meter, and from here a telephone line is here, telephone line is here, right. So, this is the thing. So, in this case this is your this distance, if I make it here only, right, if I make it here only. So, this is this between these 2 telephone line, it is 1 meter, from the symmetry from here to here it is 1.5 meter, right, sorry 0.5 meter, right, and here to here it is 2 meter, that means this distance is 1.5 meter, right. That means this distance from here to here, it is 1.5 meter, right, and this is 2 meter, and this is your D2. Therefore, D2 is equal to root over 2 square plus 1.5 square is equal to root over your 6.25 is equal to your 2.5 meter, right. That is not D2, D1, this is D1 not D2, this is D1, this distance is actually D1 not D2, D1, right. So, this D1 is equal to 2.5 meter. Similarly, when you calculate D2, right, in this case this is your what you call, this is your 2 meter as usual, right, and this from here to here you have to find out that here it is 1.5 and this is your 2.5, right. So, this portion is this your here to here, if you take this to here it is 2 and from here to here it is 0.5. So, from this distance is 2.5. I mean if you take like this, hold on, right, this is your P2 and this is your 2 meter and this is your telephone line 1, this is T1, right, this is T1. So, this distance is 2.5 and this is 2 and this is your D2. Why it is, why this 2.5 from here? From here to here it is 4. So, here to here it is 2 and between this telephone line is 1. So, from here to 0.5. So, 2.5. So, D2 is equal to actually 2 square plus 2.5 square, that is approximately 3.2 meter, right. So, first you have to calculate these distances. Once these distances are computed, then you have to find out that flux linkage your of telephone line T1, right. So, next is that your flux linkage of telephone line T1, right. So, lambda T1 I write 0.4605 I log 1 upon D1 minus I log 1 upon D2, right. This is the flux linkage of telephone line T1, right. So, both you have to consider this current, here it is I, here it is minus I, right. So, lambda 2 will be coming this much of milliweber turns per kilometer. Similarly, for lambda 2 you find out it will become 0.4605 I log D1 upon D2 milliweber turns per kilometer, right. So, this is I am writing, no, you have understood one current is I, another is minus I here also. Now, total flux linkage of the telephone circuit when I am doing it, we are writing lambda T equal to lambda T1 minus lambda 2. This is leaving up to you that why minus, you think these two equation lambda 2 and lambda 2, but you think total one in other way, right, then you will get the answer. Now, lambda T is equal to lambda T1 minus lambda 2 is equal to, it will come 0.921 I log D2 upon D1 milliweber turns per kilometer. This is up to you, right. Little bit I will leave it up to your imagination that why, right. So, that means flux linkages we got. Now, mutual inductance, then mutual inductance M is equal to lambda T upon I, right, is equal to 0.921 log D2 upon D1 millihenry per kilometer, right. Now, D2 we got 3.2, D1 2.5, substitute here, you will get 0.0987 millihenry per kilometer. So, voltage induced in the telephone circuit J omega m into I, omega m, L omega is the reactance, m omega is that mutual, or what you call, we define mutual one. So, this is actually mutual reactance. So, Vt is equal to J omega m into I, right. I is given, I think 120 amperes I is given, right. Therefore, magnitude we are putting only, J remove magnitude omega m into I. So, 2 pi 50 Hertz system 50 into 0.0987 into, it is milli is there. So, that is why into 10 to the minus 3 into 120, because current magnitude is 120 ampere volt per kilometer. So, that voltage into telephone line 3.72 volt per kilometer. This is the answer. I hope this problem is you have understood, right. Next, another one. This is also from your basic concept. This is something like, it is numerical, but it is something like theory, right. So, example 4. So, all derivations we have seen and all you have gone through also. Now, look at this example, right. Derive the formula for the internal inductance of a hollow conductor having inside radius R1 and outside radius R2, and also determine the expression for the inductance of a single phase line consisting of the hollow conductors described above with conductors spaced a distance d apart. So, first is the internal inductance of a hollow conductor. We have seen internal inductance of a this thing what you call that solid conductor half into 10 to the power minus 7 Henry per meter, but we have to find out the internal inductance of a hollow conductor, right. So, this is the cross sectional view of hollow conductor. Inner radius is R1, this is that inner radius, and outer radius is R2, and same as before at a distance x, right. We have taken a small region dx, and length is 1 meter. So, I told you that area will be dx into 1 square meter, right. Now, using equation 14, that coming from that Ampere's law, Hx at a distance x, that your Hx is equal to Ix upon 2 pi x, right, that magnetic field intensity. Now, using equation 15, we are assuming the current density is same, that means at a distance x, that your Ix divided by x pi x square minus your R1 square is equal to I divided by pi R2 square minus R1 square. So, at a distance x, area of this one is pi x square minus pi into x square minus R1 square, pi into x square minus R1 square is equal to I, that solid portions area, that I upon pi R2 square minus R1 square, current density same. From that only, that is equation 15, Ix we write x square minus R1 square divided by R2 square minus R1 square into I, right. Therefore, this Ix you substitute here, right. If you substitute, then Hx will be x square minus R1 square divided by R2 square minus R1 square into 1 upon 2 pi x into I, right. Now, not going back to the equation, I have already marked here, using equation 18 and 19 you will get that differential flux linkage, that d phi x is equal to mu 0 into Hx into dx. That means here only, that means in this region only the differential flux your d phi x, right, is equal to mu 0 into Hx into your dx. Actually, it is, I should have written dx into 1, that length is 1 we have taken, but all these things you have gone through, so no need, right. So, Hx into dx, right, multiplied by 1, not doing it, right. Therefore, d lambda x, that d lambda x is equal to that fractional, your what you call that fractional trans ratio, we have said, no. So, d lambda x is equal to x square minus R1 square divided by R2 square minus R1 square into d phi x, right. So, earlier we have given the term that fractional trans ratio. So, here also flux linkage, because it is internal. So, it will be, this is the fractional term, right, this is the fractional term. Earlier we made x square your what you call x square upon R square, but it is a hollow conductor. So, this term is coming into d phi x, right, is equal to your this is understandable, because for solid conductor we have made it, at that time it was x square upon R square, there is no R1 R2, only one radius R, but in this case it is hollow conductor. So, this is the fractional term into d phi x. So, this is the flux linkage. Now, this d phi x mu 0 Hx dx you substitute here, Hx you substitute Hx here, and d lambda x already is there, d phi x is equal to substitute Hx, and finally you put everything here, you will get mu 0 into x square minus R1 square by R2 square minus R1 square whole square into I upon 2 pi x into dx, right. So, integrate, because it is hollow conductor, so integrate from R1 to R2. If you integrate, it is integration is your job, right. I am giving you the final expression. So, this integration you can do it, a simple integration, right. You just break into the square term and just divide this by x, then integrate, right. So, in this case you will get mu 0 into I upon 2 pi R2 square minus R1 square whole square in bracket 1 upon 4 R2 to the power 4 minus R1 to the power 4 minus R1 square into R2 square minus R1 square plus R1 to the power 4 natural log ln R2 upon R1 bracket close Henry per meter. This is L internal, therefore, sorry, this is lambda internal, right. So, this is actually not Henry per meter, this is flux linkage Weber turns, right. So, in this case L internal is equal to lambda internal upon I, right. So, divided by I, lambda internal by I. So, this I should not be there. So, this is the expression of upon some simplification, right. The expression will be something like this: L internal half into 10 to the power minus 7 into 1 upon r 2 square minus r 1 square whole square and bracket all these terms, right, Henry per meter, right. This can be further simplified, right. So, it is 0.05 divided by r 2 square minus r 1 square whole square and bracket all these terms will come in milli Henry per kilometer, right. So, using equation 27, we know that L external, that already we have derived that equation 27. If you go back, 2 into 10 to the power minus 7 natural log ln d up r2 Henry per meter, and this one although I have written is equal to 0.4605 log d upon r2, as in this expression natural log is coming, we did not convert it to the log. So, this portion we will not use here, right, only this natural log we will use. So, these two if you add, inductance of a single hollow conductor of 1 kilometer length, if you add L internal plus L external. So, you add both and simplify, you will get L is equal to 0.2 and in bracket all these terms r 2 square plus r 1 square by 4 into r 2 square minus r 1 square minus r 1 square upon r 2 square minus r 1 square plus r 1 to the power 4 r 2 square minus r 1 square whole square ln natural log r 2 upon r 1 plus ln d upon r 2 milli Henry per kilometer. So, this is the expression for internal inductance and this is the expression for the total, right. So, this is for the your what you call internal total inductance of the hollow conductor. So, when conductor is hollow, so naturally the expression also totally different, right. Next, this is another example, right. So, here I have to I have to take many examples for you, otherwise problem will arise, right. All I mean varieties of problems, such that whatever possibility problems have come to my mind, I have made it, right. So, determine the inductance per kilometer of a transposed double circuit 3-phase transmission line shown in figure 16, right. Radius of each conductor is 2 centimeters. So, this is actually a transpose, this is the configuration given A, B, C, then your A dash, B dash and C dash, right. Between A and C dash and A dash C, the distance is given 7.5 meter, right, and this vertical height is given 4 meter, here also it is 4 meter and total is 4 plus 4, so 8 meter. So, all other distances like your D1, D2, D3, D4 or you have to compute, right. So, D1 is equal to 7.5 already given, right. Then D4 is equal to, it will be 9 meter, just I am telling you from here, this is 7.5, this side is your what you call this side is, this portion is 0.75 and this side is also 0.75. So, D4 is equal to 7.5 plus 0.75 plus 0.75 is equal to 9 meter, right. Similarly, D2 is this one, this is 7.5 and plus 0.75 and this is 4. So, D2 is equal to that square root, this is half square root, that is 4 square, that means this 4 square plus this is 7.5 plus 0.75 whole square to the power half. So, D2 is 9.17 meter, because first you have to find out all the distances, right. Then you have to find out another distance, the D, this distance, this D, this symmetrical. So, AB or C dash B or BC or A dash B dash, this all distances are same, symmetrical. So, you have to find out D. So, D also, this is your if you make it like this height is 4, this is 4 means this is 4, right, and for this one, this is your, this height is 4, this side is 0.75, that is this is also 0.75 meter, right. So, that means d will be is equal to your 4 square plus 0.75 square. That is why d is equal to 4 square plus 0.75 square to the power half, that square root is equal to 4.07 meter, right. Similarly, d3 means this one, right. So, here it is 7.5 and from here to here it is 8, right. That means, d3 is equal to 8 square plus 7.5 square to the power half. So, 10.96 meter. R is given 2 centimeter, that is 0.02 meter. So, first you calculate all the distances, right. After that, equation 71, first DEQ, right. So, DAB, DBC, DCA to the power 1/3, it is symmetrical thing. So, DAB, that means between phase A and B, just previously also we have seen expression of DAB, BC, CA, same way. So, it is between DAB, if you take DAB and your this thing, what you call that, what will be that your DAB part. So, it will be d into d2 to the power half, 4 things will come, d2 into dd2 to the power 1/4, but ultimately it will be d into d2 1/2, right, because it is between the phase A and B. All 4 possibilities will be there, A to B, then your what you call your A to B dash, right, A to B dash, similarly your what you call A dash B dash, right. So, DAB and A dash B dash they are same, right, and similarly AB dash and A dash B dash they are same, 4 times it will come to the power 1/4, identical. So, that is why dd2 to the power half, 4.07 into 9.17 to the power half, 6.11 meter. Similarly, from the symmetry AB, similarly B to C, they are also same from symmetry. So, DBC is also dd2 to the power 1/2, 6.11 meter. Now, DCA only again it will come dd1 into dd1 to the power 1/4, but ultimately it will be d into d1 to the power half, because d will be repeated twice, d1 also will be repeated twice. That is why directly written dd1 to the power half. You can see yourself, so many things we have seen, right. So, it will be 8.8 into 7.5 to the power half. So, 7.74 meter, right. So, DAB, BC, CA you got. Now, DEQ is equal to DAB into DBC, DCA to the power 1/3. So, substitute all these value AB, BC, CA, you will get DEQ is equal to 6.611 meter, right, that is DEQ. Next is your equation, using equation 73, right, the DS is equal to DSA, DSB, DSC. Now, find out that your self GMD for phase A, phase B, phase C, right. So, DSA now easily you can calculate, R dash 3 is it is phase A. So, A dash no, so it is D3 is there, right. So, R dash D3 to the power half, right. So, similarly for DSB also that phase B, right. So, it will be your R dash D4, because B dash, it is B to B dash distance is D4. So, it is R dash D4. Similarly, DSC will be R dash D3 to the power half. So, C R dash C to C dash, right. So, same distance, A to A dash, C to C dash, symmetry, same distance, D3 means C to C dash is also D3. So, it is R dash D3 to the power half, right. So, so multiply this DSA into DSB into DSC, if you multiply all, it is coming R dash D3 into R dash D4 to the power half. After multiply and simplify, you will get this one. Therefore, DS is equal to the DSA, DSB, DSC to the power 1/3, that is this one is this one. So, R dash D3 into R dash D4 to the power half whole to the power 1/3, right. Substitute all these value, R dash is 0.7788, R is 0.02, similarly here also, and simplify, you will get DS is equal to 0.4 meter, right. So, DEQ obtained, DS also you have obtained. Next is that formula directly use the inductance per phase, L is equal to 0.4605 log DEQ upon DS millihenry per kilometer. DEQ 6.611 and ds 0.4. So, 0.56098 millihenry per kilometer. So, this is the answer, right. Next example we will take for composite conductors. We have seen no inductance of derivation we have seen, right, but here also we have to obtain this. So, I have taken little bit small example. If I take bigger one, then it will take more computation. So, determine the inductance of a single phase transmission line consisting of 3 conductors of 2 centimeter radii in the go conductor. Go means you assume current is going inside into the page, right, and 2 conductors of 4 centimeter radii in the return conductor as shown in figure 7. So, earlier for the mathematical derivations we have taken group of conductors X and group of conductor Y. We have taken in group n number of conductors, general formula, and group Y we took m number of conductors, right, and total mutual possibilities will be n into m, and for each group it will be for the group X n number of conductors. So, n into n, that is n square possibilities, and for the group Y m number of conductors, within that your self one m into m square possibilities, but mutual will be n into m, right. So, this is composite conductor X, right. Here A, B, C 3 conductors are there. So, here n is equal to 3, right, and here 2 conductors are there. So, m is equal to 2. Distances are given, A dash 6 meter, A to B 4 meter, B to C 4 meter, and you have to find out that your what we call inductance, right. So, before going to that, here I have written group X n is equal to 3, group Y m is equal to 2, and mutual possibilities m into n total is 6, right. So, you calculate all the distances, dc a dash under root 8 square plus 6 square is equal to 10 meter, then dc b dash under root 4 square plus 6 square is equal to 7.211 meter, right, and all dA dash, dAb dash, dBa dash, dBd dash all are given, right, all are given, right, and this is the now using equation 54, first you find mnth root, right. So, in that case what will happen, that dm the mutual one, right, mutual one, all possibilities dA dash, dAa dash, dAb dash. So, dAa dash, dAb dash. Next you will take dBa dash, dB dash, dBa dash, dBb dash. Next we will take C, dCb dash, and dCb dash and dCa dash. So, all mutual possibilities you take to the power 1 upon mn, right, and here m is equal to 2, n is equal to 3, right. So, here it is written mn is equal to 6, but directly I have not written here 6, I have just written mn, right. After that I am putting here mn is equal to 6. So, now getting this example, how to compute dm now will be clear to you, right. Now, put all these values, you will get 7.162 meter. Similarly, using ds x group self GMD of group X you have to compute. So, using equation 55, look at that, you will get dAa, that is basically it will be r dash, later we will see dAa dash, dAa, then dAb, then dAc, dAa, dAb, dAc, then you take B, dBa, dBb, dBa, dBb, then dBc, then you take C, then dCa, then dCb, and then dCc, right. So, all these the n square, all 9 product, there are 9 product, and n is 3. So, it will be 9, right. So, dAa is equal to dBb is equal to dCc, I am making r dash x, we are assuming that group X conductor radius is Rx. So, r dash x is equal to 0.778 Rx, that Rx is given 2 centimeter. So, it is basically 0.015576 meter, that r dash x, right. Once you made it, all these calculations, then dsx you put all these distances, all this you multiply, you will get dsx is equal to 0.011576 cube 4 to the power 4 into 8 square to the power 1 upon 9, 9th root, right. If you see at the power, you will get 2 plus 4 6 plus 3 9, you have to see that it is matching with this, then dimensionally is correct, then things are correct. If you have not made any wrong calculation here, right, I mean in distance calculation, but you have to check this, right. So, it is 0.734 meter. So, using 53 equation 53, this is the expression for group X conductor, Lx is equal to 0.4605 log dm upon dsx millihenry per kilometer. You substitute dm and dsx, right. So, you will get Lx is equal to 0.45 millihenry per kilometer. Now, for mutual case, the dm will remain same when you will calculate Ly, the mutual distance will dm will not unchanged, only dsy will be different. Here also, here you have 4 conductors, sorry 2 conductors in your this thing, where it has gone, just here. Here you have 2 conductors in composite conductor y, 2 conductors, right. So, in this case, here it will come dsy, dA dash, then dA dash b dash, then dB dash a dash, then dB dash b dash. So, dA dash a dash, dA dash b dash, dB dash a dash, dB dash. So, dA dash and dA dash a dash and dB dash b dash, right. That is dA dash and this is ry dash, right. So, again radius of the group y conductor 4 centimeter. So, it is r dash. So, 0.7788 r divided by 100, you have to convert to meter. So, 0.03115 meter. So, dsy is equal to, put all these values, it will be because repeated values, same value, that is why 0.03115 into 4 to the power half, because 4 will come twice, this one also will come twice, that is why it is half. So, 0.353 meter, right. So, similarly, that means next is your use this Ly, same formula, dm will remain same, right. So, 0.4605 log dm upon dsy, 0.4605 log 7.162 upon 0.353 millihenry per kilometer, right. So, if you solve, Ly is equal to 0.602 millihenry per kilometer. So, total inductance of this thing Lx plus Ly, you add both Lx and Ly, 1.057 millihenry per kilometer. From this one thing you have noticed that for when number of your what you call number of conductors are more in a group, that inductance is less 0.455, because here 3 conductors are there and group y 2 conductors are there. So, if you put more conductors, so inductance will become less, hence the reactance, right.